Hi everyone, welcome to WISC 10D, and this is going to be on Module 19.4 of our new textbook, and we're going to be talking about surface area of spheres. So first I just want to say thank you guys so much for persevering through some really extra long flipped classroom videos in this last unit. I'm really proud of you guys for wading through all of those examples and just keeping your chin up through the length of them. I promise you this one is going to be short and sweet, okay? So pause for applause there. Okay, so we are going to talk about exploring here and developing the surface area formula. As always, you know that I like to tell you not just the formula, but kind of how to go about getting it. So what we need to do is we need to think of a three-dimensional sphere, as we have in our picture here. And what they've basically done is they've taken really tiny and really skinny little pyramids and approximated just a few of them. There's only 3 of them you can see there. But you're to basically visualize that you've got a whole bunch of pyramids coming down to a point, they call it the apex of the pyramid, that all of those points come together at the sphere's center, okay? So, of course, we know that the formula for the volume first of a sphere, the volume of a sphere formula is base times height over 3, or rather, I'm sorry, the volume of a pyramid formula is base times height over 3. And so when we talk about the approximate volume of each of these particular pyramids that we have here, I hope you can agree that the height of the pyramids is going to be equal to the radius of the sphere. So in part A, we're going to take our base times height over 3 formula, and we're just going to adjust it a little bit to that the volume is base times height over 3, which is going to become actually base times radius over 3. Okay, so then as we continue this exploration, it says, okay, now remember that there are n pyramids of those kind of coming together at the center. All I would need to do there would be to multiply that number br over 3 by n. So that's n times base times radius over 3. That's the approximate volume of the sphere in terms of basically adding up the n pyramids that come together at that sphere's center. Then what I'm going to do is I'm going to think in part C here of saying, okay, well, if I set that formula that I just came up with, n times b times r over 3, and I set it equal to the volume of a sphere formula. Remember, that is our 4/3 pi r cubed formula for the volume of a sphere. And now what we want to do is we basically want to highlight here and try to get the n number of bases of those pyramids all by itself. So I would need to take 2 steps to solve for n times b. I hope you can agree. To get rid of my denominator of 3 here, I'm going to need to multiply both of these sides of the equation here by 3. And that will cancel out my denominators. And then what I will be left with at that point is n times b times r is going to equal 4 pi r cubed. Now, like we said, what we're trying to solve for is the total number of pyramids bases, because remember, the bases, it says here, it says the bases rest against the sphere's surface. So if I can add up all of the bases of the pyramids, now there's only 3 in this picture you can see here, but we're to consider there's almost like an infinite number of them coming out from the center. But if I can add up all n of those b's, if you will, and so that's why we're trying to get this n times b piece alone, then what we're going to have is the surface area of our sphere. So we've got one more step here to get our n times b all alone. And when we do that, notice our r's are going to cancel out over here. And one of the r's is going to cancel out with the r cubed. So my r cubed is going to go down to r squared. And so at this point, I can now say that n pyramid bases, or n times b, is going to be equal to 4 pi r squared. And then, guys, that is your surface area formula for a sphere, 4 pi r squared. So that's pretty simple. Let's go ahead to our first example on the next page. And in our first example here, we've got again our formula reiterated for us at the top of the page there. 4 pi r squared is what we're going to be using. So we've got a spherical tank that's 21.5 feet in diameter. Please do make note of the units that are being used there of feet. The corrosion-resistant alloy skin of the tank is 1/8 of an inch thick. Take note of that as well. Hopefully you can see that those highlighted units means we're going to need to do a conversion here, so keep that in mind. How much alloy is used to make the tank to the nearest cubic inch? Okay, so because they said inches, we're going to need to make sure we first transfer that foot measurement into inches. So you can see what that process is in part A. They've taken half because we were given, of course, we were given diameter, okay? So we're going to take half of 21.5. We're going to get 10.75, but remember, that's still in feet, gang. So then I need to multiply by 12 inches over 1 foot to get the feet to cancel out. And so my radius is just 129 inches, okay? So now in part B, what we're going to do is we're going to take that number 129 that we just came up with and substitute it in for the radius in 4 pi r squared. So write in 129 in your empty block there. And then we are going to go ahead and multiply that all out on our calculator. If you want to do an intermediate step of leaving pi in the mix, that's going to be 66,564 pi. Or if we go ahead and get an approximation there, 209,116.9734 is what my calculator gives me there. And then we need to take that number, the 2009 number, and we need to figure out the amount of alloy to the cubic inch by going ahead and just multiplying by its thickness. And the thickness, remember, is 1/8 of an inch thick. So at this point, 209,116, oops, let's try to make that a little bit easier to see, 116.9734 times 1/8 is going to give us our final answer, and it does say to round to the nearest cubic inch, so I'll show you that rounding process. We're going to have 26,139.62, and to round it, we're going to take and round to the nearest cubic inch, so that's 26,140 inches cubed. Okay? Hopefully you can follow that process. Remember, you always have the opportunity to pause and to use the arrow keys. I sent out a text today about this through remind.com, so make sure that you make use of your keyboard buttons so that you can go back and forward in the video easily, just a couple frames at a time. If you missed anything that I said and need to back up. Awesome thing about flipped classroom. Alright guys, at this point it is now your turn, so these are the on your own problems. You want to follow the model of example 1, and you're going to be this time finding the surface area of both a basketball here and a baseball, okay, and it's asking how much material is needed And that's basically an application of talking about what's the surface area of each of these different sized spheres. So I'll leave you to that. Just a quick reminder, since it does say circumference here, guys, remember to look up the circumference formula and use 2 pi r for the circumference formula, since you know you're going to need r eventually in the surface area formula. Okay? So pause the video, and once you're sure you've gotten your on your own answers to check with what's written into your whisk packet, you can go to the next page. On the next page, we have the surface area of composite figures. And just like before, we're going to be going ahead and painting the outside surfaces here. So you can see the process they've walked you through for A, B, and C here in example 2. Once we have basically a hemisphere plus a cylinder and finding the surface area of that, they break it up into area 1, area 2, and area 3. Okay, so find the area of the base of the cylinder. That's this bottom part that would be painted, or right hand edge, if you will, right hand face that would be painted, and that's just pi r squared with a radius of 5, as you can see from the diagram, so 25 pi. And notice the instructions here do say make sure that you are finding the answer both in terms of pi and to the nearest tenth. So keep the pi symbols in there as long as we can. So 25 pi is what we have to begin with. Then in part B, we're going to find the area of the curved surface of the cylinder. Well, you guys, the curved surface of the cylinder is otherwise known as the lateral area. And if I remember from my cylinder video, that's 2 pi RH. And so R is the same as we had in part A there. So a 5 for our radius. And the height of the cylinder is 14. So multiplying that all out and again leaving it in terms of pi, I am going to have 140 pi. Then I'm going to find the surface area of the hemisphere. Please keep in mind that's a hemisphere. So we do need to take into account the 1/2 of 4 pi r squared formula now. So 1/2 of 4 pi r squared is going to actually be 2 pi r squared. So 2 pi, and then my radius is still 5. R squared. Please make sure in order of operations you think about squaring the 5 first, so 25, then times the 2, and then of course tagging the pi symbol on. So this is going to turn out to be 50 pi centimeters squared. And then of course the composite is going to be putting those 3 values that we just came up with in parts A, B, and C together. So our 25 pi, our 140 pi, and our 50 pi are going to be all added up to get me 215 pi, because remember I need it in terms of pi as well as an approximation to the nearest tenth. Now at this point I can use my calculator and I can get 675.4. And that'll be it, you guys, for today, okay? I will see you tomorrow for some practice with spheres, and this is our very last section of the year. Way to go, you guys. See you in a little while.